Okay, so today we are going to see that the converse to Fermat's little theorem is false. And for that, let's go back to the statement of the theorem. What the theorem says is this. Say P is a prime and A is an integer such that P does not divide A. Then the following congruence is true. A to the power P minus 1 is congruent to 1 modulo P. Now, you can clearly see that this is after all an implication. In fact, most of the theorems are only implications, some of them are double implications, in which something is given and something we are claiming is true. So here, the given part, the hypothesis is this, and this is the conclusion. Now, you can also interpret the hypothesis as a statement about the number P. Say you have already chosen the number A and you are considering some integers P. I am not saying that P is prime or anything. A has already been chosen and P is an integer which does not divide A. So P has this condition imposed on it that it's an integer which does not divide A positive integer. Then how does the implication look if I write it as an implication? It will then look like this. For that chosen P, say I choose P, A has already been chosen and P is an integer which does not divide A. This is how the implication then looks. P is prime implies this congruence is true. So what will be the converse of this? The converse will be this. If the congruence is true, then P must be prime. For that chosen A and with the condition that P is an integer which does not divide A. This is not true. This is not always true. Not always true means in general it's not true. And that's what we are going to prove today. And actually we are going to prove this by showing that 2 to the power 340 is congruent to 1 modulo 341. Now the role of P is being played by 341. Note that 341 is a positive integer which does not divide 2. Here 2 plays the role of A. But the congruence is true. In fact, this is what we want to establish. And at the same time, in spite of this, our P now is not prime. That's because this is 31 times 11. So once we prove this, the converse to Fermat's little theorem will be false. Now to establish that congruence, we will need an elementary lemma. So let us first see the lemma. So this is the lemma. Let A be an integer and P, Q be distinct primes. They are different primes such that A to the power P is congruent to A mod Q, and A to the power Q is congruent to A modulo P. Okay, so A is some integer and P and Q are distinct primes for which these two congruences are true. Then A to the power PQ is also congruent to A, and now the modulus is PQ. Okay, so let's prove this lemma. The proof is elementary, but still we have to see the proof. So let's start with this congruence. Since A to the power P is congruent to A modulo Q, so by one of the properties of congruences, we can raise both sides to their qth power. The left hand side will then become A to the power PQ, and the right hand side will be A to the power Q. But from Fermat's theorem or its corollary, we already know that A to the power Q is congruent to A modulo Q. Also, from Fermat's theorem, we have this. The original statement of Fermat's theorem doesn't have Q here, but Q minus 1, and here we have 1. However, for that, Q needs to not divide A. That condition is there, but we already have seen that this congruence is true even when Q divides A. This is true for any integer A. So now you use this congruence and that one, and use the fact that congruence, the relation congruence is transitive. Hence, this is congruent to A modulo Q, i.e. if I write this as a divisibility relation, then Q divides A to the power PQ minus A. So if we instead start with this congruence and then raise both sides to their pth power and go through an argument similarly, a similar argument, then we will get this other thing. P divides this. And after this, we are going to use the fact that P and Q are relatively prime. Because they are distinct and they are prime, so their GCD is 1. And hence, by a previous result, their product will also divide this integer, and that previous result is this, corollary 2 to theorem 2.4. Now, by corollary 2 to theorem 2.4, PQ divides A to the power PQ minus A. So if you write this as a congruence, you get your claim. Mod PQ. Okay. So now that we have proved the corollary, lemma, so let's get to the actual thing. We can write from here itself. We now want to show that 2 to the power 340 is congruent to 1 modulo 341. Note that 341 is 31 times 11, so it's not prime. Okay, now how shall we start our thing? I mean, how shall we go for showing it? Note that because we have this power of 2 where there is a 0, so 2 to the power 10 we can try to see that. If one does the calculation, one gets this number 1024. It's not a very big calculation, and it turns out that this is 31 times 33 plus 1. So if one divides this number by 31, the remainder is 1. In other words, this power of 2 is congruent to 1 modulo 31. Is congruent to 1 modulo 31. Hence, what about 2 to the power 11? This is 2 times 2 to the power 10. This is congruent to 1 mod 31. So, this will be congruent to 2 times 1, which is congruent to 2 mod 31. Okay, so the 11th power of 2 is congruent to 2 mod 31. Next we consider the 31st power of 2. This also you can express in terms of 2 to the power 10 like this, 2 times 2 to the power 10 whole cube. Okay, now you can see that just like dividing 2 to the power 10 by 31 gives you remainder 1, dividing 2 to the power 10 by 11 also gives you remainder 1, which becomes clear from this equation itself, because 33 is 3 times 11. So this is also a multiple of 11, just like it's a multiple of 31. But you can actually get this congruence, that this is congruent to this, that is 2 to the power 10 is congruent to 1 modulo 11 from Fermat's theorem itself, because 11 is prime, which does not divide 2, and 10 is 11 minus 1. So anyway you are getting this congruence, which is congruent to 2 modulo 11 now. 11 is our modulus. So do you see that now you have that type of 2 congruences? 31 is a prime number and so is 11, and they are distinct. Where is it? 2 to the power 11 is congruent to 2 mod 31, and 2 to the power 31 is congruent to 2 mod 11. So we can apply the previous lemma. So by the above lemma, 2 to the power 11 times 31 is congruent to 2 modulo 11 times 31, or 2 to the power 341 is congruent to 2 modulo 341. Now we can cancel 2 from both sides of this congruence. However, you must make sure that whatever you are cancelling should be relatively prime to the modulus. Yes, it is. 2 is relatively prime to 341. 2 is 2 and 2 does not divide 341 and 2 is prime. That's why they are relatively prime. Or you can also say that 2 and these are relatively prime because the only prime divisor of 2 is 2, whereas the prime divisors of this number are 11 and 31. There is nothing common. Okay. Now, cancelling 2, we get this. And this is what we wanted to establish. This shows that the converse to Fermat's little theorem is false. The congruence may still be true, which we have as the conclusion of Fermat's little theorem, but the modulus is not necessarily prime. So let me just end with this itself. After this, there are some other things like Mersenne prime, and some things are there which we will see in the next number theory video. And tomorrow also we have an upload, and tomorrow we are going to start differential equation from Ross's book. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.